From before, we know that r equals r cosine theta times I plus r sine theta times j, and v equals negative r omega times sine theta I plus r omega cosine theta j. Now, knowing that theta equals omega t, which follows since theta of 0 equals 0, we can replace theta with omega t here and here, getting these expressions for the r and v vectors. Now remember, our question is, what's the a vector? Without looking at this, you should, using this information, be able to determine what the a vector is. Okay, we'll get to that in just a second. I'll go over here and comment just a little bit more on this theta equals omega t, since theta of 0 equals 0. We've already addressed this. In general, theta equals omega t plus theta naught, where theta naught is your starting point. Omega t is how far the r vector rotates in time t. Okay, so omega is the number of radians per second, t is the number of seconds, omega t is the number of radians of rotation of the vector r. We add that to wherever it started, to whatever angle it had when it started, and we get its angle at time t. So in general, we would replace this theta with omega t plus theta naught. The model we're working with right now, theta naught is 0, and that's what we're going to continue with. You might think as we go through this, or go back through it yourself, what would happen if we had omega t plus theta naught? What would that change in the results that we're getting here? Turns out it wouldn't change very much, but there would be a difference. Okay, now, how did you get A? Hopefully you paused and done that yourself. A is the acceleration, which is the derivative of v. So we just take dv dt and we get this. And that's very simple. Using the chain rule, the derivative of sine of omega t is omega times the cosine of omega t. So we're going to have negative r omega squared cosine omega t, which is what we have here for the I component. And similarly, the derivative of the cosine of omega t is negative omega times the sine of omega t, which gives us this. And then we can note that this vector is closely related to the r vector. Now you ought to make sure you see that relationship. How is this a vector related to the r vector? I'm going to tell you, but you should have thought this through. You have the cosine of omega t here, you have the cosine of omega t here. Sine of omega t here, sine of omega t here. You have r here and here, you have r here and here. But you have the negative signs here, and you have that omega squared. So what do you have? Well, if we factor out the negative r omega squared, if we just factor out a negative omega squared, we end up with our position vector. Follows that the acceleration vector is negative omega squared times our r vector. Now this is something you're very likely to have encountered in your pre-calculus and dynamics classes, or your vector calculus and dynamics classes, those of you who are taking those courses. So this ought to be something you grasp very quickly. Okay, so in any case, the acceleration vector is negative omega squared times the r vector, and we can depict that fact on our unit circle. Now here I've used a different point than I used before for the reference point, for the terminal point of our r vector. We have our r vector, which is r cosine omega ti plus r sine omega t j. Angle is theta, which equals omega t. Velocity vector is v equals negative omega r sine omega ti. And I'm not going to read it to you. It's the same as what we have up here. It's perpendicular to the r vector. And we have the acceleration vector. Since the acceleration vector is a negative multiple of our r vector, it's going to point back toward the origin. The r vector points from the origin to our point. The acceleration vector is directed from the point toward the origin. So there's our acceleration vector, and of course we can write out what the acceleration vector is. And again, I'm not going to read that to you. It's the same thing I read to you here. Okay, so there's our picture of the r, v, and a vectors for something that's moving around a unit or a circle with constant angular velocity. A question came up about, well, it isn't actually, a comment came up relevant to a situation where the object might be speeding up or slowing down in the circle, in which case the a vector still is equal to what it's equal to. But that's now just a centripetal acceleration vector, and you have another component of acceleration in the direction of motion. Again, the videos I posted about a month ago work through an example of that, which you might find relevant both to what we're talking about here in this course and what you're talking about in a couple of your other courses, those of you who are taking those other courses, vector calculus, dynamics. Okay. Now, the next question that was raised is, what are the x components of these three vectors? Because as I interjected between the video before this one and the last one, the x component of the r vector gives you a model of the simple harmonic motion of an object along the x-axis, moving along the x-axis with an amplitude r. The vx vector, the x component of the velocity vector, is the velocity of that point moving along the x-axis, or that object moving along the x-axis. And the x component of the acceleration is the acceleration of that object as it moves along the x-axis. Okay, well, what are the components, the x components of the position, velocity, and acceleration vectors? Well, here they are. And they're easily observed just from these functions. Right there's the x component of the r vector, it's the I component of the v vector, and the I component of the a vector. And we've written those down here. What about the y components? I mentioned before, I didn't go through the details of it, but we could also use this for the simple harmonic motion of an object moving along a vertical line, along the y-axis. What are the y components? Well, here they are. You should be able to do this very easily now. Ry equals r sine omega tj, r omega cosine omega tj, and negative r omega squared sine omega tj for the acceleration. And those are just read off from the j components of the position, velocity, and acceleration vectors. We noted up here, we didn't need to take the derivative of the r vector to get this result for the velocity vector. We reasoned this out just based on what we know about the relative angle of the r and the v vector. But had we done dr dt, we would have gotten exactly the same thing. So just verify for yourself the derivative of this is equal to this.